For as long as humanity has turned its gaze skyward, one question has endured above all others. Are we alone? It is perhaps the most profound inquiry in the whole of science. And the search for an answer has become the defining investigation of our age. But where, in a cosmos of almost incomprehensible scale, does one even begin? When the crime scene stretches across billions of light-years, instinct alone will not suffice. What is needed is evidence. Precise, irrefutable traces that something living, has left its mark upon the universe. Scientists call these traces biosignatures. Life's fingerprints, written across an entire world. But the definition demands rigor. A biosignature is not a suggestion. It is not a possibility. It must constitute proof, incontrovertible evidence that a biological process, and nothing else, is responsible. Every conceivable non-biological explanation must first be considered, examined, and eliminated. Only then can the fingerprint be trusted. These signatures take many forms. An anomalous gas drifting through a distant atmosphere, oxygen, for instance, abundant here on Earth as a consequence of 4 billion years of photosynthesis. Or strange geometries in ancient rock. Fossilized structures. Minerals that only living chemistry can produce. And perhaps most tantalizing of all, technosignatures. The electromagnetic whisper of a civilization. Yet the universe, it turns out, is a masterful forger. Take oxygen. On Earth, it speaks unmistakably of life. But bombard a planet with sufficiently intense ultraviolet radiation, and something remarkable occurs. Water molecules are torn apart in a process known as photolysis, hydrogen escaping to space, oxygen accumulating in the atmosphere. No organism required. A false positive of the most convincing kind. It is the sort of problem that occupies the minds of astrobiologists in the small hours. And so every candidate biosignature must pass a rigorous three-part examination. Reliability: have all non-biological explanations truly been ruled out? Survivability: will the signature endure long enough, across cosmic time, to be found? And detectability: do our instruments, peering from light-years away, possess the sensitivity to see it? Only what passes all three earns consideration. The question then becomes, where to look? With hundreds of billions of stars in our galaxy alone, the sheer scale is humbling. But probability offers a guide. The most numerous stars in the Milky Way are red dwarfs, comprising some 85% of all stellar bodies. They are, by any measure, the dominant architecture of the galaxy. And they offer something our own sun cannot: time, in extraordinary abundance. Where the sun will exhaust its fuel within 5 billion years, a red dwarf burns with such frugal restraint that it may persist for trillions. Trillions of years in which life, should it arise, might find its footing and flourish. The most common stars. The longest lifespans. It sounds, one might think, almost ideal. There is, however, a complication. Because red dwarfs burn so cool and dim, a planet must orbit in uncomfortably close proximity to receive sufficient warmth to sustain liquid water. That proximity brings consequences. Tidal forces lock the planet in place, of one hemisphere facing perpetually towards the star in scorching, relentless day, the other turned forever away, locked in an eternal, frozen night. There may be solutions. Climate models suggest a sufficiently dense atmosphere might circulate heat between the hemispheres, carving out a narrow temperate band at the twilight boundary. But there is a more fundamental hazard. Young red dwarfs are volatile. They erupt with colossal stellar flares capable of stripping a planet's atmosphere away entirely. Great starspots can dim their luminosity by nearly half for months at a time. The environment, for all its promise, is one of extraordinary instability. And so the red dwarf dilemma persists: abundance and longevity on one side of the scales, violence and extremity on the other. The verdict remains, for now, unresolved. Yet if the challenges are formidable, the tools being brought to bear upon them are remarkable. The James Webb Space Telescope, the most powerful eye humanity has ever turned to the heavens, is already reading the chemical composition of distant atmospheres. The Europa Clipper is en route to Jupiter's moon, where a vast ocean lies concealed beneath kilometers of ice. And on the horizon, the Habitable Worlds Observatory, conceived with a single, audacious purpose, to find another Earth. Through all of it, one principle must remain paramount, anchoring the entire endeavor. It is not enough to find something that life could make. The evidence must be something that only life could make. The investigation is very much alive. And somewhere out there, written in the light of distant worlds, the answer may already exist, patient, silent, waiting for the moment we possess the wisdom to read it.